So the core task of what we will do in this course is to teach a computer to learn a function. This function will be learned from a set of examples. We start with a data set D, basically the set of input and output. These outputs are the desired outputs. We want later, when the computer sees new x's that follows the same distribution as D, can predict this desired outputs. So assume, just to formalize this, that we have n of these examples that we can use to learn this function. So this function should be flexible enough that can characterize all of these relationships that are between x and y. So for example, a data matrix of n rows, and each one of these observation or samples has d features. In, for example, a classification task, we want to classify each one of these samples into a class 0 or 1. So y will take a shape like a vector of n dimension of 0 and 1s. But we can also have a regression where basically f is a function from x to a real value. So like I said, we want f to be flexible enough that when later we give an xi that we never saw in the training, but we know that xi is following the same probability as training data, we want our flexible f to predict the desired output. So why this is a difficult problem? One main reason is f should be flexible, like I said, but at the same time, we can have many f that can satisfy this condition. However, we want one of them that maybe is most suited to our case or performs best in this specific context. So to come up with that f, sometimes we need to give the algorithm an inductive bias to basically go toward the f, the type of f that we want. In our previous courses, for example, in linear regression, we chose a linear model to be the class that our f belongs to. So this type of f basically assumes the world is linear, and it can fail when we have a complex data that is not following that world. We will call this situation a high bias situation, where we are very off from the real data. The model is off. The model is simple, so it will have low variance, but of course, this strong bias is not desirable. In deep neural networks, we have a weak bias, meaning that f is much more flexible. This flexibility lets it learn complex patterns, but of course, this comes with a risk of overfitting. So we should be always alert on how to deal with this. This is a case of high variance and low bias. And sometimes neural networks are actually able to memorize the entire training data. And then when you deploy into the test data, they will perform poorly. Okay, so let's assume a class for our f that we want our f to follow that class. So oftentimes we will parameterize this family or this class by a set of tuning parameters. So W, you can think of W like a tuning parameter. And when we have a given input, this function will give us yi, right? The desired output. So when we have a very good tuning for such function. So let's call this good tuning our estimation of that W or that set of parameters. So we want to find or estimate such W that can work well to this unseen data. And we want to be able to assign a label that is an accurate label or good enough label that is close to what we want. So we want to learn this W. Then the problem of learning here is finding or estimating these W's. And then we want such function to be able to do inference for us. So inference is prediction of this label in the unseen data. So these are the lingos that we are going to use. So with that, I'm going to focus on the linear regression. Just to do a recap during this, I will call some of these concepts that we learned there, and we are going to use later during the course. So in linear regression, we assume a linear relationship between y and x. So we wrote this linear relationship like this. So basically what this gives us is a hyperplane in the space of x. And for example, in the case of classification for an x that is two-dimensional, nice Euclidean two-dimensional space, this will give us a linear plane that basically separate the space in two parts. So for example, maybe the positive part can be from this part. Like I said, the equation that determines this decision boundary is this linear equation. So what we want to completely define this hyperspace is the weights and this bias. So the weight specifically defines the slope of this hyperspace. So let's talk about how we can determine or estimate W's that can do well on some loss functions that we want for this specific linear case. We need to basically say what is not a good hyperplane, or we need to quantify an error in this regression case. So one standard choice is the mean squared error. So MSE, or mean squared error, can be written as 1n, the number of samples, I, minus the function that we estimated. So here yi is the real supervision signal, or the desired output. And we are going to use the squared error over all of these samples or examples that we have. So remember that we want the loss to be minimized over all of these examples. So we call this an MSE error, and I'm gonna just assign a value here, a loss that is a function of W and B. So sometimes during the course, you will see that I want to simplify the algebra, and I basically consolidate W and B into one W. And how I'm doing this, I basically augment X that initially, if you remember, in this case of linear regression, was a n by d matrix. I add a column of ones, basically augmented to that, which will be the initial X, and then the column 1, which makes the new X n by d plus 1. So by doing that, I have a new W, which is now augmented with B, which is previous W, and a B at the end. So this way, the algebra will be easier. I basically got rid of B by sending it into the W. And this way, I can rewrite this equation. So this way, everything will be easier and simpler. Okay? So whenever you saw that, doesn't mean that we don't have B. It means that B is already in W. Even in the neural network architectures, follow the same notation. Okay, so going back to this loss function, I again simplify by basically write this in a matrix form. If you remember, in linear models, we found the best W's, W in the sense of ordinary least square, by minimizing this loss over all of these W's, right? So to do that, we took the gradient and we forced it to be 0. And we found the W that makes this equation or satisfy this equation. In the linear case, this can be done in analytic way. So this is nice. This is a closed form analytic equation. We can solve this for small data sets and when linear function is a good function. The complexity of this solution is in D3. And that means that for very high dimensional data, this will be very expensive. And on the other hand, if we have a complex model, we cannot do this. This is only doable when the linearity is satisfied. So for what we want during this course, this is not reachable. We cannot use this because we have none of those luxuries. Our data sets are often very large and our models are not linear. So we have to come up with other ways of doing this, finding this W. And as we will discuss later, we will use a different form of gradient descent. So going back to what we did here. So basically what we are doing, we are minimizing the distance between our Y and our prediction using the model. So if I want to give a geometric interpretation to this, basically we want to minimize the distance between Y and the model prediction for all of our examples. And we call this basically the error for each one of these examples. And here in this case, this is a vector E. And what happens here is basically we have a hyperspace defined by our linear regression. And like I said, this is the column space so of X give us a basis for this hyperspace, and we want a prediction that is living in this column space. We cannot go outside of that, and we predict the value of Y using this prediction. So if Y happens to be outside of this hyperspace, we cannot basically exactly go there because that will fall outside of this basis. So our linear regression, because it is living in the column space of X, cannot exactly predict Y, but it will project Y into the hyperplane, and there will be some error remaining that our model is not able to explain. So that's the error that, as I said, it is perpendicular to column space of X. And we want to minimize this error by adjusting the slope and the bias, our model parameters. So continuing on the linear regression and the linear model, I want to introduce the concept of bias variance and how we do this trade-off between these two. So to do that, let's write the error of a found f that we found previously. So in a more general case, this error is the expected error that even we get a new example that we never saw, but it is following the same distribution as the data that we trained our model on. And want to minimize the error of such unseen examples using our model. We do our best using the data that we have. So we have the same loss function, and to simplify the algebra here, let's just write it this way. Basically use the properties of expectation. We can write this in this way. So this is a decomposition of that error of the model for this unseen data. So like I said, there will be some reducible error that we cannot do anything about using our linear model. So that they will remain. So we cannot do much about that. Anyway, so let's focus on this decomposed components. The first part we call this the bias. And the second part is the variance. The bias, what bias does is basically measures how far is the average model prediction from the truth. And this distance is because of some inherent assumption that we did that limited the model expressivity to basically predict that. For example, in this case of linear regression, linearity is that limiting assumption. And we can say a simple model on complex data is systematically wrong, or in other words, it is underfitting to the data because of this basically observed bias. The variance, on the other side, measures how much the prediction would change if we collect a fresh training set. In other words, the model's sensitivity to sampling noise. On the other hand, variance measures how much the prediction would change if we collect a fresh training set. That means that how much the model is sensitive to the noise in sampling. Error from sensitivity to such small fluctuation in the training set can be accumulated, especially if our complex model somehow fit to this noise. So we call this situation overfitting. So I keep saying that we evaluate the model eventually in data that the models have not seen. So that's why we split this data set into different splits of training data, validation, and test. So basically what we do is we allow the model to see the training data completely, and we use the validation data to decide for the trade-off of the bias and variance, and basically hope for the best when we prepare the model this way. When the model is deployed to the test data, when the model has not seen it, it will perform the best. So that's how we usually deal with the data splitting. And like I said, in the case of if we have the model complexity on the x-axis and we increase the model, and oftentimes in the training, when we increase the complexity of the model, we have a much better fit over more complex models. So this will be the error, and this is the fit to the training data, right? So, but we kept a validation data to basically tell us how good is this, how much this fit will stand the test of unseen data. And oftentimes what we see in the linear models and other models like that is a validation error that behave like this. So the reason is basically that this area is the area that we have this underfitting. We can still improve the fitting, but then after that, when we continue adding complexity to our model, there will be an area that we overfit. By overfitting, I mean we basically we let the model to learn fluctuation in the data, the noise in the data that is not necessarily part of the signal. And once we deploy the model to this validation data or later in the test data, we will see the model is overfit and there will be a high variance. So if I want to add the variance here, initially the variance will be small because of the simple model, but then the variance will start increasing and at some exploding. So that's the usual U-curve of bias and variance. So it's important to know that this U-shaped diagram is not a law of nature. So we can do techniques, we can deploy better models that can reshape this. I mean, for example, we can have, of course, more data that can allow our model to have a better training. We can have ways to make sure our model is not getting more complex for no reason. So we inject some regularity into the model. So we call this regularization. Of course, this will need some intuition, some maybe even domain knowledge that basically allow us to come up with some engineering decision. For example, the type of regularization or during the training. For example, we can think of decaying weights. We can think of early stopping of training. So those are techniques that we'll talk about during the course. So another technique that is also can be discussed is the inductive bias that I explained previously. In the choice of the model family, possibly have a better inductive bias in our choice of model selection. So this way we can again improve the situation that is plotted in this U-shaped diagram. So examples of these techniques we can talk about, for example, breach regression that we learned in linear models, Lasso, for example, and other types of regularization in training neural networks, for example, dropouts, data augmentation, ensembling, that all basically do the same thing. And what they do is to nudge the learning dynamics to go toward parameters that behave more consistently across possible data sets. So that's what we do here. If we fix the model, meaning that if we choose our inductive bias and if we choose the type of regularization, adding more data will improve the model performance. For example, if we have n examples, the variance will decay with a rate of 1/n. And it's important to note that the bias will not be changed by adding more data. But if we change the model itself, then we can talk about the bias changes. So that's the two most important distinction between these two and how we are controlling them. So just to complete the discussion, let's go back to our way of finding W. And we said that we are going to use this loss function. And why we are choosing this loss in the case of linear regression, we can zoom into this. And basically, the assumption is we have a linear process where we can explain using a linear model, and there is a noise that is Gaussian, and our linear model is not able to explain. So there is a noise, and it's a standard noise, and this implies a conditional probability, meaning that having x, w, and b will give us y that is following a normal distribution because of that noise that the linear model cannot explain. So this conditional probability basically tells us that how likely it is to see this desired output given x and the model parameters. So we want to maximize this likelihood. How can we write this? We basically can write this in this way. We want every sample to be likely. So for all samples, we have this likelihood, and we want to maximize this. So we know from before that it's the same as maximizing the log of these probabilities, which in that case, if we take log of this, so if I call this the MLE of data given W and B, we can also work with log of MLE, which is the log of this product, which becomes sum of all of these log of probabilities. Right? We have a Gaussian distribution. We can rewrite this as a Gaussian distribution, which you can write this way. And if you plug this in, you will see that this sum will be, this is basically the loss that we will deal with. If you remember, I said we want to maximize this MLE, and here the log MLE, which is equal to minimizing this least square. loss. So that's why we chose least square in the linear regression. So why I said that, basically I want to say that the choice of loss requires some research. Loss basically dictates the performance of the model. We want to tell the model that you're a bad model because you are not doing good in this basically set of example, and the model has to find a way to improve. And the loss is the guiding principle. So choice of loss is important, and we have to talk about that. Okay, now we have a clear objective. We want to minimize this loss function. And to do that, we can play with our weights or tune the knobs of these weights that give us this minimum value. So we are looking for weights that can minimize this function, this loss function. What's the challenge here? The challenge is in modern neural networks, W can be billions of parameters. And this loss function also can be a very complex and non-convex function. So what's the solution? Before presenting the solution, I want to invite you to think about the geometry of this. So basically, assume we have parameter space W, and we have a value of loss. Of course, this is very simplified, but let's assume we want to find this minimum here. And to do that, assume you are here blindfolded, and you want to basically find that point. So you start from this peak here, and first you feel the slope under your feet, and that's basically like computing the gradient, the slope of that curvature here. And then you start taking steps. So here, for example, you start taking steps this way, and you continue until you reach to some point that basically you feel like this is the valley. But we know that there is a better solution here. So how can we get there? So the mathematical formulation of this hill climbing intuition is called gradient descent. And the idea is, in each step, we update the previous parameters or the previous weights of our neural network with one step of this gradient. That is a function of the previous weights, of course. Okay, here, assume we have the previous weight and we want to update this. So we need to compute this gradient here. And as we know, the gradient can be computed from this loss function by looking at the average gradient per example. So we need to compute this for all of these examples that we have in the data. What's the issue here? So the issue is we can have a very large data set. In modern data sets, like I said, we have millions to billions of examples. On the other side, large modern neural networks can have very, very large set of parameters. We are thinking of possibly billions of parameters. So computing one gradient step like this requires looking at every single example, and that can take a long time. And for training a neural network, we need to take thousands of steps to get to this point that we desire. So we need to change our strategy to scale this up. So instead of just doing a gradient descent, we are proposing stochastic gradient descent. So the idea is we don't really need the exact gradient. A good approximation is enough. So that means that instead of solving this very expensive sum, we approximate this using much smaller random mini batch, meaning that instead of meaning that instead of doing this for all examples, we will do it for a subset of these examples that we choose randomly. We call this subset a batch, and a batch is much smaller than the total number of examples that we have in the data. So we are thinking of some values like, for example, 32 compared to an n that can be 1 million. So why this works? Why opting for a much smaller batch size can give us still a good gradient step? So the key idea is this mini batch gradient is unbiased. In other words, the expectation of a gradient step, direction and size is equal the total gradient. So the proof is actually very simple. You can think of it basically, if we randomly sample each example, and that means that each example has an equal chance of being selected, the expected contribution of example I to each mini batch is basically the average over all of this data set. So a few things to consider here that can deviate from the theoretical proof is we are looking at each example and basically randomly sample each example, but we are not putting it back. This is not a sampling with replacement. There are practical reasons for this. One is we want to look at all of these examples as much as possible and not looking at an example multiple times. And also we want to basically have an average contribution equally distributed for all of these examples. However, this sampling without replacement somehow affects this proof. So this proof is not real, is for the case of sampling with replacement. So just consider that. And you should know that this is an active field of research on how to make this more theoretically rigorous. So if we want to give an algorithm for this stochastic gradient descent, so we have to first shuffle the training data, then divide the training data into mini batches of some selected size B. Then for each mini batch, we do the following. We first compute the gradient, then we average them, then we update the parameters. And we repeat this process for multiple epochs. So this will give us a random, really noisy step toward the optimum. And the main reason is because we are randomly choosing these subsamples or batches. And this will give us a noisy step. And this noisy nature of stochastic gradient descent has two maybe more general zone of behavior. When we are very far from, let's say, we have two weights, our neural network for some reason has two weights, and there is like a very nice spot that the values that these two weights can take, and our loss will take some minimum value. So this is like maybe a hole in the space, the valley that we were talking about. So when we are taking the stochastic descent outside of this kind of close area to the optimum, all of these steps are somehow directing toward that, meaning that's basically the idea of unbiased direction, that no matter what you do and what random sample you do, the gradient descent has a pretty confident step toward the optimal. So it may not be the direct path, but in average, if you take all of these steps, you will get there. And then once you are there, that area is not that certain anymore. And this is called region of confusion for these SGD steps. And this may look like this is not desirable, this is maybe not economic. Basically, there we can have directions that are not necessarily to this optimal point that we want to target. But as you will see, this actually gives the algorithm a nice property of that helps the model to avoid getting stuck in poor local minima. And also, this leads to solutions that generates better to new unseen data, prevents the model from memorizing the training set, and that basically, if you remember, that will help to generalize for unseen test data. So basically, this equips SGD to escape this bad minima. Okay, so we discussed how to come up with a scalable way to compute these gradient steps using a smaller subset or a batch of data. So as you see, we have two engineering decisions here. What can be a good step size and what can be a good batch size. So as you will see, you during the training of your neural networks, those two decisions can change the performance of the neural network training. So alpha, or the step size, is also known as the learning rate, and it controls how big step sizes are. Typical learning rates will be values, for example, between very small values to 0.1. If I want to give you a rule of thumb, I would start with 0.01 and then adjust this based on the behavior of my training. So why this can matter, the size? Well, imagine the same hill climbing analogy. If you start from here, for example, a small step size can be very small and very slow toward the optimal. A large step size, on the other hand, can jump and overshoot somewhere else, and that also may not be optimal. But if you come up with the just right size or the good progress value, can be something that quickly give you conversions to optimal weights. Okay, so now let's look at the choice of batch size. So if we choose the batch to be small, talking about maybe 1, which is one example in each batch, up to 32, this is considered as a small batch size. The good thing about this is highly noisy. So like I said, we like this. This means that we explore the space of parameters better. And that can lead to better generalization, right? So this is a plus. What's the disadvantage of this? Well, like we said, this is slow. The convergence will be slow. This is not efficient for our GPUs. And if we increase the batch size to some medium size, something between the standard value 32 to 256, this is considered a good balance. And also this is actually very efficient on hardware. However, the noise is not as much as before, and this is not good because we may skip or not discover better local minimums. So what if we increase the batch sizes to large values? This can give us faster conversions, but the exploration is less than before. and in this case we may overfit. So far we discussed this vanilla version of SGD. There are ways to improve this algorithm. The main reason, the main problem with this SGD is, like we discussed in the choice of batch size, they can oscillate in narrow valleys and they can progress slowly because the only thing that they have to control their conversions is this alpha here. So we can add more options to improve this. One option is adding momentum. By adding momentum, I mean, so instead of the initial W's, we update the momentum based on the gradient. So this is known as velocity update, which then will do the update on the parameters. Here we call beta momentum coefficient that can take values typically between 0.9 and 0.99. So the intuition for this momentum-based SGD is basically imagine like a ball rolling downhill. It builds up speed in consistent directions and rolls through small bumps. So this way it will be more consistent and may have the more and faster desirable convergence properties. One variation of this modern SGD algorithm that we will use a lot during the course is known as ADAM. So ADAM stands for Adaptive Moment Estimation, and it combines momentum with adaptive learning rates for each one of these parameters. Like I said, momentum helps SGD to navigate these narrow valleys, basically escape from them efficiently by accumulating velocity in consistent directions. In this case, basically what we mean by momentum is the algorithm accumulate these past gradients, and adaptive rates basically scale the learning rate for each parameter based on gradient history. There is a bias correction where accounts for initialization bias. So as you will see, ADAM will be our go-to option most of the time because of all of these properties. We may employ learning rate schedulers that basically control these step sizes and reduce them for more fine-tuning over the training. So if we want to give a summary to this section, we start from some W. Most of the time we start from random values for W. Then for each epoch, we basically look at the data and extract a mini batch. And for each one of these mini batch, we calculate the loss, and this is known as the forward pass. And this basically gives us the loss. And then we need to have a way for calculating the gradient, which is basically, as you will see in the next lecture, we call this a backward pass. That gives us the gradient and the average gradient for that mini batch. And then having that, we can update the weights and then check if this is a convergence. If not, we have to continue for the next epoch. So this is the no. If it's converged, then we are done.